Okay, everyone. Uh, maybe may, I might be somewhat in that boat with you, Mr. Enoch, but um, we're just gonna try and keep on chugging along. um, Welcome back to Steel Design during the first day of March. A couple of housekeeping items. So I know I said that my target was to get the exam graded by today. I wasn't able to complete that. My apologies, but I have a fair amount of free time after class today, so I'm hopefully going to try and either chug it out or complete a large portion of it because I kind of need to just sort of knock it out. So my target is to have that done on Wednesday. Now you're getting your first bolted connection assignment today. And so last time what we did is we talked a lot about the background. I have a little bit more background I have to talk about today in regards to the layout requirements. And then we're just going to start rocking and rolling and do a full-blown analysis example today. And then we're going to do another analysis example on Wednesday. That one is going to be maybe a bit trickier because it's going to be a splice connection. So you kind of have to do a little bit of thinking before you just chug right into it. But a lot of the math is fairly repetitive. But let's just sort of get right into it. And what I want to do is I want to start, let me get my mouse over here. I want to start with this, okay? There's a lot going on here on this slide, but this slide basically summarizes everything we talked about on Friday. So to start, when we talked about bolted connections, we said there are two classes of bolted connections that we handle as steel designers, and that is a bearing type connection, which relies on the bolt coming into physical contact with the plate inside the bolt hole. And so the two limit states that are relevant to that are the shear capacity of the bolts themselves and then the bearing capacity of the plates. And so we call that bolt shear and bolt bearing. For bolt shear capacity, we went through the variables and what can affect bolt shear capacity. So there's, the grade of bolt. Are we dealing with a A325, A490, all of that. The thread condition, whether or not the threads are included, whether or not they're excluded, whether we're in a single shear scenario, whether we're in double shear, what's the bolt diameter. And so we even went through a very basic exercise. Like if I had I don't remember what it was, but I think it was like a 3/4 inch A325 bolt in single shear, threads excluded or something like that. What's the capacity? And we went through the exercise, but then we said, hey, there's this, which is one of the most valuable design aids in the manual, which is on page 7-22, that will just tell you what the shear strength is. And so we're going to use that today to determine the shear strength of the bolts in a given connection. And then there's bolt bearing. Now, unfortunately, there are some design aids, but they're not as user-friendly as honestly just chugging it out. And so the bolt bearing capacity, so to compute the bearing capacity per bolt, we're going to use this equation in gray. And so we take the minimum of 1.2 LC TFU or 2.4 dB TFU. And everything in that expression is pretty simple. Other than the LC, that takes some doing. For the LC, we have two different LC values. So LC is our clear distance. It's the distance basically from edge of steel to edge of steel. So if we're talking about an interior bolt, it's the distance between edge of hole and edge of hole. So we take S minus a hole diameter. And then for the bolts on the edge, we take the edge distance minus half a hole diameter because we're concerned of the distance between the edge of the bolt hole and the edge of the plate. Now this bolt bearing check is a capacity check, so we're talking about these distances in the direction of loading. And so when we're looking at a bolted connection, the edge bolts are going to be here, and these are going to be the interior bolts. And so that connection down there below has 4 edge bolts and 16 interior bolts. And so basically what we would do is we would have an RNE that we would compute a capacity for an edge bolt, and then we'd have RNI, a capacity for an interior bolt. And if we wanted the capacity of the whole thing, we would just say 4 edge bolts plus 16 interior bolts. And then don't forget we have to adjust by phi RN in the end, and phi is 0.75. And don't worry, we're going to have an example on that today. Now, the one thing that you're not going to like me very much, I apologize, it is what it is. We're in bolted connection land, and in bolted connection land, we are assessing the actual hole itself. Remember, in tension members, we took the diameter of the bolt and we added 1/8 of an inch. Now, we did that because we weren't really adding 1/8, we were adding 1/16 twice, okay? 1/16 was to account for the actual physical dimensions of the hole. The hole is a little bit bigger. And so that's what we're assessing, the actual hole itself. So we use the diameter of the bolt plus 1/16 of an inch. In tension member land, we added an extra 1/16 because we weren't sure about that lip of material transmitting load to the rest of the member. But we're not looking at the rest of the member. We're looking at the connection region itself. So we only add. So you'll notice, and this is something I actually started doing this year teaching the class, I'm actually using different terminology. So I'm calling it, DH. When we did tension members, we did DE, the effective diameter of the hole. So we're using the actual physical dimensions. So I changed that up a bit to make it a little clearer for you as the student, especially, since we're doing this online, I wanted to make sure I was being as clear as possible. Now, any questions before we start talking about layout requirements? All right. Now, what I'm talking about in this slide is all about strength. It's all about taking the connection and looking at the bolts that are being used and how far they're spaced from each other and from the edge in order to determine a capacity, a load that the connection can withstand. Okay. On top of all of that, there are also limits regarding the spacing of the connection itself, not for strength, but for real life serviceability issues. And so we need to talk a little bit about those connection layout requirements. One, because we want to ensure that our connections meet these requirements as well on top of strength requirements, but also we're going to use these connection layout requirements for design purposes, okay? So what we're talking about when we say connection layout requirements is we're basically looking at two things. We're looking at how far apart the bolts are spaced from each other and how far apart the bolts are from the edge of the plate, okay? And there are reasons for each of those, and we're going to get into why. And they have nothing to do with strength, okay? The reasons why we have these bolt spacing limitations are for other very practical considerations as well. So let's start off, and what I'm doing here is I'm basically listing this out the way that they are listed in the spec, okay? And so I want everybody to follow with me in the manual on this. So we're in section J3.3. We're on 16.1-130. So I'm going to go ahead and turn to that. I want everybody to turn to this as well because I want you all to see where I'm getting this. So I'm on 16.1-130, and if you're looking on the webcam, so you should see on the left page, it says table J3.3, and then we're at the bottom of the page right here where it says minimum spacing. And you might as well leave this manual open here because we're going to be looking at minimum spacing and then minimum edge distance and maximum spacing. We're going to be looking at all of these here in a second. So I'll give everybody a sec to turn to that, and then we will get to it. I'll give everybody a sec. So we're on 16.1-130. Okay. I'm going to assume everybody found that because, and to be clear, one thing I'll mention, I'm not asking you to turn to this just for, the old exercise in high school where it's a poem and you have everybody read a line of the poem or a paragraph from the essay. There is actually a section in this region of the manual we need for evaluation purposes. So hopefully you can find that. But right now, let's just take each section one at a time. So let's start off with minimum bolt spacing. So reading directly from the code, the minimum spacing, the distance between the centers of standard, oversized, or slotted holes shall not be less than 2 2/3 times the nominal diameter of the fastener. However, the clear distance between bolt holes shall not be less than D. So long story short, our minimum distance is 2 2/3 times the bolt diameter or 8/3 times the bolt diameter. I actually kind of prefer this way. I have had students plug into their calculator 2 times 2/3 times, I don't know, 3/4 of an inch, and that is not 2 2/3. That's 2 times 2/3. So that doesn't work out. So yeah, the limit is 8/3, so 2.67, if you will. Now, there's also a user note here that says that the preferred spacing is 3 times the diameter. Sometimes engineers will use the preferred. Sometimes engineers will use the minimum. In design land, I'll tell you which one I want you to use, if I want you to use preferred or if I want you to use minimum. And then as we get to the end of bolted connections, I'll talk to you about some very common practices that you find in bridge engineering land, and building engineering land, not just bridges, but steel land in general. I'm curious though, because this is a class and I do want a little bit of interaction. Why do you think this limit exists? Like, who cares if the bolts get too close together? What do you think issues would arise if the bolts got too close together? And nothing to do with strength. It has nothing to do with strength. So if you start saying that the connection gets weak or isn't able to hold up the load, that's not what we're talking about here. Mr. Adkins.
Is it possible that if they're too close together, if one fails, then it may start a chain reaction?
You're talking about strength again. I'm not talking about that. No, that's fine. That's fine. But it has nothing to do with strength. It has nothing to do with failure. What Mr. Geis said is really, the answer. And what Mr. Riggs is saying, that again kind of gets to strength. I'm talking about if you have bolts that are too close together, how do you get a wrench around the bolts to tighten them? It has nothing to do with strength. It's simply that if the bolts get too close together, you're not going to be able to put the connection together. There has to be some degree of distance between the bolts so that you can actually get a wrench around them and tighten them. And so 2 2/3 times the bolt diameter is a basic minimum to ensure that you can actually put the thing together. So now, Mr. Blizzard brought up fabrication tolerances. Let me say this. That actually isn't the biggest deal with the bolt spacing issue. Like, you tell a fabricator where to drill holes, they'll drill them. They'll drill holes wherever you want. But workmanship and fabricator preferred practices do play into not the bolt spacing limit, but the limit on the edge distance, and there is an issue there. So why do we have a minimum bolt spacing limit? Because if the bolts get too close together, we can't go out in the field and get a wrench around them and tighten them. So that's really the issue there. Now, as for the minimum edge distance, this gets a little bit more into what Mr. Blizzard was referring to. So if the bolt spacing is how far apart the bolts are from each other, the minimum edge distance is how far the holes can be from the edge of the plate. And so if we read the spec, and this is one thing that you're going to have to start to get used to a little bit in structures land, and this is not unique to steel design or concrete design or buildings or bridges. Sometimes there's a treasure hunting expedition that you can find when referring to specs, because I open up section J3.4 and it says the distance from the center of a standard hole to the edge of any connected part shall be found in a table. So it's like you look up a section, then it says, okay, I need to go to this section. And then this section says I need to go to that section. That can happen a lot in structural engineering and in any document, any code specifying body. Sometimes you have to hop around a bit. And so that just happens. So if you have your manual open and you literally turn the page to 16.1-132, you should find this table. It should say table J3.4, and table J3.4 is the minimum edge distance from the center of a standard hole to the edge of a connected part. And so what we've got is, I don't want a yellow highlighter, I want a pen. Okay, so here's a plate, here's a hole. We're talking about, this distance here. That's what we're talking about. LE minimum. And honestly, this, again, has nothing to do with load. It doesn't matter if this distance is in the direction of loading, perpendicular to loading, it doesn't matter. This is all about preferred fabrication practices. I mean, read the user's note at the bottom, and the user's note states, the edge distances in this table are minimum edge distances based on standard fabrication practices and workmanship tolerances. Has anybody in the class done any type of woodworking? I'm just curious. Any wood? And I mean, I know we're not talking about steel. We're talking about woodworking. Or have you ever operated a drill in your life? If you have, imagine this, okay? Imagine this scenario. So imagine you've got like a sheet of plywood, okay? And, you're looking at the corner here. And imagine you tried to drill a hole like right there. Kind of tough, isn't it? It's kind of tough to actually get a well-defined hole that close to the edge of the sheet of plywood, right? You would think that if you were trying to teach somebody how to do woodworking, and I reference woodworking because usually you find most people, if they've not done any like welding or metalworking in their life, that they might have operated a battery-operated drill at some point in their lives. But if you were trying to teach somebody how to, operate a drill and they were going to be drilling into wood, you might tell them, okay, you got to have at least, some distance between that hole and the edge of the piece of plywood so you actually get a well-defined hole. Well, that's what we're talking about here. Again, it has nothing to do with strength. It's just about workmanship, okay? And so, for instance, if I have, let's say, a 3/4 inch diameter bolt, that hole better be 1 inch from the edge of the plate, and that 1 inch is from the center of the hole to the edge of the part, because if you're drilling, you need to know where the center of the hole is to start drilling. Does that make sense? Any questions there? Yes, this isn't too bad. This is all common sense stuff. Now, here's the kicker. All right, this is what I'm curious about. I'm curious about, we've talked about minimums. What about maximums? Okay, so what about maximum spacing and edge distance? Now, it almost, you might think it doesn't really make a lot of sense, when you first start thinking about this. If I put all this, fabrication practice stuff in your head, why would anybody care if the bolts get too far apart? Why would anybody care if the bolts are too far apart from the edge of the plate? Well, let's think about that, okay? I want to talk about this question right here. We talked about what happens if bolts get too close together. If bolts get too close together, then you can't tighten them. What do you think happens? What issues would arise if bolts get too far apart? I'm curious what the chat has to say about this. And the hint is it's kind of indirectly on the slide. It's kind of indirectly mentioned in the spec if you think about it. But I'm curious, what would happen if the bolts got too far apart? I think I heard somebody's microphone on. Less room for more bolts. No, I think it would make more room because you'd have a whole lot of space between them. But there's another issue.
Is it really about how much connectivity between the bolts, the plate the bolts were initially attached to, and the plate behind it?
Sort of. All right, so and the connections are taking on more load individually. That's a strength issue. This has nothing to do with strength because that's about how much force and load the bolts can withstand. This has nothing to do with strength either. Let's talk about this practically. When you take two plates and connect them together with a bolt or a series of bolts, the idea is to compress those plates together, right? Well, if those bolts are really far apart, you think this might happen? So you've got, here, let me do it like this. So you've got, you know, a plate here. Maybe what happens is you get a little bit of a gap between your plates because there's not enough bolts in between to connect them. That they're not fully connected, that there's a little bit of a gap. Now that gap, I'm really exaggerating what that gap would look like in real life, but with a big space between the bolts, there would be a little bit of a gap between the plates. Why would we be worried about that? Why would we be worried about a gap between the plates? Boom. And Mr. Blizzard and Mr. Mitchell and Mr. Ball are all saying the same thing. What could get into that gap? Water. Well, I guess I should have written the 2 as a subscript, but I didn't have time. Water could get into that gap. And if water gets into the gap, that could cause corrosion. Okay? That's what I was saying earlier. Like if you look at the code, it's actually sort of talking about corrosion in the spec, and that's the issue. Okay, so if you want the be all end all answer, why are we worried about bolts getting too close together? Because we're worried about being able to tighten them and get a wrench around them. Why are we worried about bolts getting too far apart? Because if they get too far apart, water could get in there, and if water gets in there, that could cause corrosion, and that's no good. Okay. In fact, if you look at the limits, there are actually 2 different limits depending upon the surface condition. So, for instance, we allow the bolts to get a little bit further apart from each other if the member is painted. If it's unpainted or it's weathering steel, then we have more stringent requirements. So, if we look at the spec, let's take a look at the spec. Let's look at this. Let's see if I can do a blue highlighter. Oh, I don't like that. That's a little dark. Let's just go with yellow. Okay. So first off, we have, you know, this right here, the maximum distance. Oh, goodness. The maximum distance from the center of any bolt to the nearest of edges, or the nearest edge, shall be 12 times the thickness of the connected part under consideration, but shall not exceed 6 inches. So what that first sentence is saying is that the maximum edge distance is either 12T or 6 inches, whichever governs. In this case, that's, you know, the minimum of those 2, and that has nothing to do with the corrosion protection system. Is it painted or is it unpainted? That, you know, the code says I don't care about that. That's your limit on maximum edge distance. But for bolt spacing, we have 2 bullets, a bullet A and a bullet B, and dependent upon your surface condition, we have different requirements. What I'm saying for us in this class, we are always going to go with the lower one. We're always going to say that I don't care, you know, unless otherwise stated, we're going to assume the worst. And we're going to assume that members are unpainted, which is pretty common in building applications. Like if you look at the column behind this partition in my office, there's not going to be any paint on that steel. It's just going to be raw steel. And so if I'm spacing out connections for that column or for any of these beams in this building, I'm most likely going to use this limit, which is either 14 times the thickness or 7 inches. So the maximum spacing comes from that. Okay, so I'm just reading the spec and writing a little pretty equation for that. Does this make sense? Does anybody have any questions on that? That's a good question. That's a good question. There are, let me say this, not here. There are other provisions for galvanized members later on that can affect other surface conditions, but not here. And if it was me, I would probably, if I was dealing with a galvanized connection and I had to make a decision, I'd probably go with that one because that, I mean, you are providing a corrosion protection system with hot dip galvanizing. However, if I was in connection design land, this limit probably wouldn't impact my design anyways, and that'll also become clear when we get into design land. So ultimately it won't really matter, and you'll see when we get into design later. I don't want to. I'm trying to be somewhat efficient in how I deliver it. I don't want to load on too much all at once. So it won't matter. It'll matter later, but not now. So here's I put a nice little side here. This is a summary of all of the layout requirements. So for bolt spacing limitations, we have a minimum spacing, a maximum spacing, but there's also a preferred spacing. When we're assessing a connection to try and see whether or not it meets the spec, we're going off of minimum and maximum. Because this preferred one is just in a user's note on the side. It's not actually code spec. The minimum and maximum are going to be what you're checking. So we're going to be checking that and seeing whether our spacing falls in between those two. As for edge distance requirements, the minimum, there's no pretty formula. We have to look it up. We have to look it up in table J3.4. But the maximum, we can write a formula for that, and it's just minimum of 12T or 6 inches. And the other thing on this one right here, this one assumes unpainted. I'm getting ahead of myself. So this lower one assumes the worst. So if you had a painted member, that one would need to change. But unless otherwise stated, we're always going to assume that in the class. Okay. Any other questions before we get into an example? Now, just so you're aware, this is actually the same example that was in the slides from Friday. But what I did, I actually took the example out of the slides from Friday and I tweaked it a bit so that the values that we were using were a little more recognizable. As you can see, I think as you will see, I think it added some clarity to the example. What we're going to do is we're going to take this connection and we're going to compute the design strength of the connection according to bolt shear and bolt bearing. Now, I actually on the side went ahead and took this member and said, what's the gross section yielding, the net section fracture, the block shear rupture capacity? And I did those calculations on the side so that we can look at, well, what are the other limit states revealing for this member as well. So we have two plates, so let's take stock of what we're looking at. So a connection is always two members being connected together. That's what a connection is. So there's two identical plates that are being lapped together. So this is a lap connection. The nice thing about this problem is because the two members are the same, when I do bolt bearing checks, I only need to check one of them. So for instance, if I had a plate connected to a channel, I might need to do two different cases of bolt bearing because I've got two different members. But for the purposes of this problem, since they're both the same, we only have to do one. We've got A36 steel, 7/8 inch diameter bolts, A325. The threads are excluded. They're in single shear, so we're going to determine the capacity of the bolts and shear, and also the bolt bearing capacity of the plate. The bolt bearing one's actually the one that's going to take the time, and then we're going to determine whether or not the connection meets layout requirements. So with that, let me go ahead and get out of the slideshow. Let me get over here. Let's see, we're going to stop this share and then share this. All right, so everybody should see the illustration here. Any questions? Or I tell you what, let me give everybody a sec to sort of jot some of this stuff down while I pull this up. Oh, sorry. Technology. Moving this over here. Let's pull this back up. There we go. That's what I wanted. Okay. All right, so I will give everybody a sec to sort of jot this down, and we'll get into it. Okay. All right, so we're going to take each limit state one at a time. So let's start off with our bolt shear capacity. Okay, so what do we know about this problem? Okay, so we were told in the problem that the diameter of the bolts was 7/8 of an inch. Now, let's pop quiz everybody, see if everybody's paying attention. So we have A325 bolts. Capacity, what does that mean? What do we need to know if they're A325? Group A. Nice. Now, we were told that the threads were... So that's group AX. Okay? Now, I think I might have already said it, so maybe I spoiled it. But if, regardless, is this single shear or is this double shear? How many shear planes are running through the bolts? Oh, hold on. There's two plates. Two plates, but only one shear plane. The shear plane is what passes through the bolt. So we're only talking about one. So to put that in context, hold on. Context, if I had this, and I had bolts going through it like that. Actually, let me use a different color for my bolts. If I had bolts going through it like this, then there would be 1, 2 shear planes. 1, 2 shear planes for bolts. That would be a double shear situation. But in this, we're dealing with single shear. Okay? So, single shear. Now, with that, this is what I need. I need you to go to table 7-1, 7-22, and tell me what is the phi RN for this situation. So we're talking about a group A bolt, threads excluded, 7/8 inch diameter bolt, single shear. What's the capacity? Okay, hold on. Okay, we got two different numbers here. And I'm getting the 30.7. That's what I'm getting. Now, that's kips per bolt. Okay? Now you got 20.4. I'm curious where you got that. Oh, no, that's the green number. Remember, we're always using the blue numbers. We always use LRFD. That's fine. That's fine. So you looked up everything in the table correctly because you found the right rows and the right columns. Just you use the green number. We're always using the blue numbers. Everybody else able to find that? I'm going to give everybody a sec, but if I don't hear anything, I'm going to assume everybody can find it. I'll move that over a bit. So that I can... Everybody good? All right. So that's 30.7 kips per bolt. So a lot of times in bolted connection land, we use a little r because that's per connector, but we use a big R for the whole connection. So how many bolts are in the connection? Hopefully that's pretty apparent. It's 4, right? 4 bolts. There we go. So therefore, phi RN would be 30.7 kips, 30 big RN, I should say, per bolt times 4 bolts. And then phi RN is, what is that? 30.7 times 4 is, I think it's like 122.8. So 122.8. Okay. And that is one limit state. I don't know if that's the answer because I have to do bolt bearing. Okay. But that is the amount of load that is required to shear those bolts. Everybody good? All right, I'm going to assume yes. Okay, all right. Now, let's look at bolt bearing. Okay, so this is the new one. All right, now I'm going to redraw the connection a bit because I'm going to make some points on some things. Okay, so here's the plate, and we're only looking one plate at a time. Oh, by the way, I missed something, but I wanted to ask. I want to make sure everybody's clear. If I do not tell you whether or not the threads are included or excluded, what do you do? If I don't tell you. Assume included. That's right. Okay, good. All right. Okay, so here's the connection, and we've got 1, 2, 3, 4 bolts. Okay, now the dimensions that I gave you for this problem were this dimension here was 3 inches, and this dimension right here is 2 inches. Okay, so if we're yanking on the connection this way, if this is how we're yanking on it, then what we're after is this dimension right here, which is LCE, and then we're after also this dimension, LCI. Okay, now we have a bolt that's 7/8 of an inch, so therefore we need a hole diameter, which is the diameter of the bolt plus what? There we go. 1/16 of an inch. So 7/8 plus 1/16, which is 15/16, right? Because that's 14/16, that's 1/16, so 15/16. All right. And so fortunately, like while there's a lot to do, it's very simple work because we have to compute an LCE and an LCI. Now LCE, so how would you do LCE? Well, you would take that edge distance, you know, that's this term right here, that's the edge distance, that's the spacing. We would take the edge distance minus half a hole diameter. And then for the interior, we would take this, the bolt spacing minus an entire hole diameter. So it's not hard, it's just you got to chug through it. So we take 2 inches minus a half of 15/16. So, you know, the fractions get to be a bit nuts. So 2 minus, what was that, 15/32. And so what I tend to do is I just tend to say, okay, 1.531 inches. I just, you know, that's close enough. And then this is going to be 3 inches minus 15/16. And so that's 3 minus 15/16. 2.06, we'll call it 3. Could somebody check that and make sure I did those correctly? While you're doing that, I want to see something. Okay, all right. So what I'm ultimately doing is I'm wanting to do this. Okay, so I'm basically trying to compute this term here, an Rn, and I need to do an Rn for basically for each bolt. Okay, so is there anything that I'm missing in this expression? So LC, I've got all my LC values. The thickness, what is the thickness of this plate? Well, we were told, let's look at the plate. So for the plate, well, do we know the thickness? I believe the thickness was given to us at the beginning of the problem. Yep, the plate thickness is given right there. It's a 1/2 inch. What about the FU value? Do we know what the FU value is? Well, no, but we were told the grade of the steel. The steel is A36. So for A36 steel, what is the FU value? 58 KSI. See, after a while, more you start doing this stuff, you just sort of remember them. You don't even really need to look them up. I will go ahead and place the reference so that we have it, but after a while you start to remember this stuff. So yeah, so for the plate, the thickness is a 1/2 inch and the FU is 58 KSI. So we have everything that we need, okay? Now, the way that I'm gonna do this is I've got a bunch of stuff that I have to compute, and I have to compute it somewhat repetitively. So here's how I do it, just to make it a little easier on myself. So I'm gonna do some intermediate calcs. This is just to make it a little easier so I don't have to keep hitting the same buttons over and over again on the calculator. So we're going to do 1.2 LCE TFU, and then we're going to do 1.2 LCI TFU. And then finally we're going to do this, got ahead of myself, this 2.4 dBTFU. So we're going to just do those three, and then we'll be able to plug into that expression here in a bit. So 1.2 times LCE. LCE was this 1.531 inches times a thickness of 1/2 inch times FU, which was 58 KSI. All right, somebody got an answer for that one? Making sure everybody's awake today. I'm going to start calling on people. There we go. Okay. So 53 point, we'll say 3 kips. That's close enough. Okay. The next one is the same thing, and I want somebody else to answer this one. The only thing is it's 2.063 here. So same, everything else is the same. All right, so 71.8. Okay. Oops. That's what I got. And then the 2.4 dBTFU, so 2.4. And we're using the actual bolt diameter here. $60.9. Okay. Okay, that's what I got. Okay, so here's why we did those intermediate calcs. So the edge bolt capacity, the RNE for the edge bolt, is the minimum of 1.2 LCE TFU and 2.4 dBTFU, which is what? The top one. There you go. So 53.3. But the RNI is the minimum of 1.2 LCI TFU and 2.4 dB TFU, which is, in this case, the bottom one, right? Because the bottom one is 60.9 compared to 71.8, so 60.9 kips, right? Now, what do we have to do from here on? Well, we have to go back to our connection. We have to ask ourselves, how many edge bolts are there and how many interior bolts are there? Well, that's pretty easy. There's, 2 edge bolts, and then there's 2 interior bolts. So in order to compute the nominal capacity of the whole section, Rn is 2Rne plus 2Rni, which is 2 times 53.3 plus 2 times 60.9. And that's going to be I'm getting like 228.4. Do I have a second on that? There we go. And then, now keep in mind, what did I forget? I forgot something. What's missing right there? It's not theta, it's the phi value. But you're right, yeah. Missing phi. That's fine. So this is 0.75 times 228.4. And so I'm getting that phi Rn is 171.3. Now, if we compare this to what we got up here, we got 171.3 kips for bolt bearing. So this is the bolt bearing capacity. And then we compare this to up here. This is the bolt shear. Which governs? Pretty easy, right? You can see that bolt shear governs, because if I yank on this connection, what's going to happen? I'm going to shear these bolts before I fail the plate. The bolts shear at about 122.8 kips. The plate fails at 171 kips. So it's clear that the plate does not govern the capacity. And if we want to know what the connection capacity is, phi Rn is 122.8 kips. That's the answer. And then, because we're running short on time, I'll do the connection layout stuff, but that's really easy. So for the connection layout, or the layout requirements, so we know that for this connection, S is 3 inches, and we have an edge distance of 2 inches. That's the smallest edge distance on any of the measurements on the connection. Well, S minimum is 8/3 times the bolt diameter, so 8/3 times 7/8 of an inch. And so that's 7/3, because the 8's cancel, and so that's like 2.67 inches. And then our S max is the minimum of 14T, or 7 inches. But if you remember, the plate thickness is a half an inch. So like 14 times a half is 7. So we know that's going to be 7 inches. Well, between these two, we have S is 3 inches. So we know that's okay, right? Because it's got to be between those two, and it is 2.67 versus 7 inches. And then LE minimum, now that one we got to look up. But LE max is the minimum. Here, I'll scroll down a bit. LE maximum, that is the minimum of 12T or 6 inches. So we know that's going to be 6 inches because our thickness is a half inch. Real quick, can somebody look up what is LE min for a bolt diameter of 7/8? Remember, that's on page 16.1-132. There we go. And so this is 1 1/8. Comparing these two, the edge distance is 2 inches. So that's okay. So we know the connection meets layout requirements, and we know its capacity. Boom. What do you think? Usually what I find is that students tend to think this is pretty easy, but I want to make sure I'm not glossing over stuff. Any questions? Because that's basically it. If you understand that, then I think your homework assignment's going to be a breeze, because the only thing that changes is instead of looking at a plate, well, usually you're right, and as we get near the end of bolted connections, I'll talk to you about some fabrication practices that are pretty common that end up meeting a lot of these requirements, but we'll talk about that later on. But my main concern is that you understand this stuff, the bolt bearing check. It's not hard. You just have to be able to grunt through it, and you have to be able to recognize how many edge bolts you have and how many interior bolts you have. If you understand that, you know all the steps, it's not hard. Any quick questions before we call it? I know we're running a little short on time. Well, not short. We're a little over. I'm going to take that as a big old thumbs up. All right. I'm going to go ahead and call it. I'm going to stop the recording. You've got a homework due Wednesday. Let me know if you got any questions. And on Wednesday, we'll do another analysis example that's a little trickier. It's a splice. Not hard. Just got to chug through it. And that's all I've got, everybody. I will see you all on Wednesday.